Recording is rolling. It's Friday, October 10th. General announcement. I did post to Google Classroom yesterday this flyer right here. Homecoming week is not next week, but the week after, starting on October 20th. Right, so these details right here, day by day, got different themes going on. So if you want to get a closer look at that, that is posted to Google Classroom. You can download that and get a closer look. So it's that. All right, your guys' forces quizzes, I did put back in your folders, so you can pick those up, or maybe you got them already. So if you do corrections, the corrections are just going to go on quarter two. It's just so late quarter one. So I'll put the correction point on quarter two. Look, I got a little bonus there. This week, you guys have been working with, actually, speaking of forces quizzes, Rich, I still got to do top scientists, but here's top scientists for forces. So awesome job. You made top scientist list.
I just don't know if I have stars.
So they got like a percent.
Yeah, that's what that means. You did really, really good.
Yes. I got a
Okay. Another detail here. We are doing picture retakes today, so if you want to do picture retakes, we're in 7th period. So last shot, probably anytime in the next about half hour or so. Okay, so this week, you guys have been doing a lab that led to this. Okay. So some force that would allow an object in motion to stay on a circular path. Right? We're going to call it centripetal force. Now, in this case, it's provided by the tension of the string, which is equal to this hanging weight right here. Okay, so same value. Okay? So that centripetal force is equal to this mass times its tangential velocity or speed squared divided by the radius of curvature. Right? Whatever this radius of curvature is. Okay? So you guys can put that together. Right, so I want to challenge you guys a bit today with looking at maybe a more realistic example could be this conical pendulum. Because guys, when you guys did the lab the last few days, could this string right here, guys, could the string be perfectly horizontal? Not actually, no. Because this mass here does have some weight, which I didn't actually draw here. And in fact, it has some weight. When you just pull down a little bit. Okay, so the string can never be exactly horizontal. Although it could be kind of close. Like if you're whipping around this pretty fast or this mouse is pretty light, or what if this was like a 5-degree angle from the horizontal? Okay. So from the vertical, that would be like 85 degrees. Guys, what is cosine of 85 degrees? Cosine of 85 degrees. Let's find out together. So whoops, sorry, that's something's off here. I'm going to reset this calculator. We try it again. I meant 5 degrees from the horizontal. Okay, I'm being silly. I meant 5 degrees from the horizontal. Let's switch to vertical limit. Okay, that's what I'm looking for right there. You guys see 0.996? Okay. Isn't that basically 1? It's very, 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 very close to 1. Okay. So the last few days, you could estimate the string as being horizontal, although more practically, it's probably more like this, especially if you had a large mass or you had to swing around kind of slowly or some combination of two. So we'll solve one of these today, which will be a good challenge question. And then I did have a couple other posters in the queue. Right, if we possibly get to these, I don't know, maybe not. We'll see where they are. Right? But I have a whole playlist of Paul Hewitt videos, so we'll end today with just those. Okay? So probably about the last 15 minutes or so of class. Right? Related to gravitation, which I haven't brought into this lesson yet, but when you combine centripetal force with universal gravitation, you can get orbits. Right? So that would be set you guys up with that by the weekend. All right, so let's solve one of these conical pendulums. Now, earlier, my AP students had a puzzle out of their book that it gave them a mass right here, right? And it told them an angle from the vertical, exactly like my poster showing, an angle from the vertical. That angle, guys, this angle, same angle? Yeah, same angle. Right. And the question was, well, there were two questions. There were two main questions. What's the tension in the string? And also, what's the speed of this mass runner, the tangential velocity, right, to maintain a constant radial size? Ooh, right, so this angle would also be a thing. Right, so you guys have the paper? So we're going to do this one challenge question today, which is kind of an extension from the lab you've been doing all week. And then we'll end the class with Paul Hewitt videos. Okay? All right, so on your paper, just draw a picture like that. Right, so get a vertical axis going. Everybody's got a vertical axis on the paper. Okay. Let's have a string here. Have a string, and we'll put a mass right here. Okay. We'll make up a value for the mass. We'll say it's something. And then let's have this going around in a circle. All right, stay on the circular path. Okay, can you guys dash off like a circular path like that? Well, it's circular. You're thinking in 3D, right? So if you look from the top, it would look like a circle. From the side, it looks kind of like oval type shape. Okay, so it's going around. Okay. It has some tangential velocity. I'll label that V. Okay, like that. And there's some angle from the vertical, I'll label theta. Okay. These will have values. Okay. So let's say I give you, so given, I'll give you four things. I give you this mass right here. I'll give you that the gravity field is, let's just stick to 10 meters per second squared. Okay, that's my sword way. I'll give you the length of the string, or good, because the string right here better have some length, right? Let's call it, oh, how about 1.2 meters? Right, so a little longer than your meter stick. Okay. And finally, I'll give you the angle theta. Okay, so this angle theta, how about 32 degrees? Just so crazy. Okay. And the mass here. Let's use number generator for the mass. 49 kilogram. Well, yeah, let's do it. How about this? 4.9 kilograms. Let's go 4.9 kilograms, and the weight will be 49 newtons. Okay. There you go. Okay. So what I want you guys to find. So a good challenge question here is going to take us a while. Okay. This will be a few steps. Find the tension in the string. F sub T. Okay. Tension in the string. Okay. And also V, which is the tangential velocity of that mass. Okay. Okay, guys, that. Okay. All right, now, while you guys are finishing popping that down and starting to think about that, what I do want you guys to see, like forest for the trees, big picture here, is that if I give you these four values, there is in principle enough information where you can solve this, right? Like if you kind of just like outside the class somehow, then you say, okay, well, I think if there's like some known mass like going around, right? Like here, this one's half a kilogram. Suppose you attach this to a string, start flying around the string, right? Okay. And it sets up some consistent angle from the vertical, and you're in Earth gravity and so on. Okay. I bet there would have to definitely be some determinable tension in the string. And furthermore, I bet there has to be some definite speed that is going around. You guys kind of see that? That's it. So next question is, well, how do you solve this? Right? And you do need your lab from the last few days. So it does have something to do with this, but we're going to do a three-dimensional extension on this. Okay? Okay, you guys ready for that? Okay. So the extension is going to go like this. Okay. As a cone, so conical pendulum, because this can make like a cone shape on it. Okay. Guys, how many proper forces are on this mass that you do have to consider? How many forces?
Three, four, two, four.
There's two. There's two. There's two forces right there. So one force is the weight pulling down. Right? Is that trying to pull it straight down to the ground? And also, what's the other force?
The tension.
Yeah, the tension in the string. Yeah. So over here, I'll do a free body diagram. So put a big old center mass right here. Okay. So the two forces are, I have mg, the weight pulling down. Let's try to label this mass. It's about 4.9 kg. Okay. And the tension, does the tension have to pull along the direction of the string? Yeah, it sure does. Right? Because which force has a larger magnitude? The weight pulling down or the tension pulling off on an angle?
The tension.
The tension. Yes. Right. Guys, make the when you're drawing this in your notes, make the tension a little bit longer than the weight. I'll label it F sub T for tension force. Right. No, for here on out, well, it would be nice to have some consistent Cartesian system. So I'm going to break the tension into components. Say, well, the tension is partly pulling up, and it's partly pulling inward. Right? It's doing both of those things. Isn't that true? Mm-hmm. Okay. Now, how much? How can I quantify how much of each? Okay. Well, that has something to do with this angle, which I just made up a moment ago. I call that 32 degrees. So, guys, what's this angle right here? 32 degrees. 32 degrees. It's the same angle, right? From the vertical. So, no, we don't know what the tension is yet. That's the first question we're trying to tackle. But regardless of what it is, what is this component here equal to in terms of the tension and the 32 degrees? What's this? Yeah, sine. It's a sine relationship. So it's the full tension force times sine of 32 degrees. Okay? And would this one here be the not the sine component, but the what? Cosine. So tension force times cosine of 32 degrees. Okay? And I know the who can tell me what's the weight of this object in newtons again?
49.
Yeah, 49 newtons. Okay. It's 4.9 kilograms, weighs 49 newtons in Earth gravity. Just like that. Okay, all right, so we're working our way around. Right, something like that. Okay, you guys good so far? Okay. Now, can you guys think of a way to make any more progress on this question? Okay, to solve for anything else? Okay, maybe I ask these questions in this order for a reason. Maybe it's easier to find tension first and speed after, maybe. Okay. Can you guys think of a way to find the tension in the string? Yeah, what do you think?
Pythagorean theorem uh, of absolute.
Okay, almost. Like, okay, so if you're proposing Pythagorean theorem, okay, I do see a right triangle here. Okay, so that could be a play, but see, I don't know exactly what this is or this is or this is because there's the f sub t in all of them, right? So ft can still be anything. Okay, so we'll hold on to that idea. What do you think?
Can we make another right triangle with length of the string and then the pole just down the middle? Or is that just not helpful?
Okay. So you're talking about like the physical length of the string. We can make a right triangle here. Yes, that'll be important later. By the time we get to this V, yeah, we will need that for later. So, guys, that line I just drew represents what property of the circle?
The radius.
The radius. Yeah, so we will need that. Okay, so this radius does have something to do with this length and this angle. Actually, I could probably write that out right here. Guys, what is radius in terms of the length and the angle?
F mt times sine of theta.
Yeah, L sine theta. Yeah. Okay. So the physical length in meters times sine of this angle would give me the radius of that circle. Okay. Yeah. So let's knock that out. Right. We might not use that right away to get the tension, but might need it later. Okay. So we'll come back to this. Okay, so I know length is 1.2 meters. Sine of 32 degrees. Yeah, let's get a hard number on that. Radius is 1.
Wait, the length of what?
The length of the string.
Oh,
Yeah, so the length of the string is 1.2 meters. Okay, so that's one of your given values. So you have a 1.2 meter long string. Okay, a little longer than your meter stick. Okay, so 32 degrees. I'm looking at 0.636 meters. Okay, and so I'll put some little thought cloud over here. Okay, so we're not going to do anything with that quite yet, but we will need that later. Okay. So how about back to this tension though? Right? And so I see two forces. There's the weight going down, which I know that value is 49 newtons for sure. Okay. Now, what is this tension holding it in place? Or maybe I should say dynamic equilibrium, so this radius isn't changing. How could I possibly find that?
Wouldn't the upward force on the F cosine 32 be equal to gravity?
Exactly. Yeah, Gavin got it. Yeah. Guys, it's this condition right here. It's the sum of the forces in the y direction, that's to say in the vertical direction. Guys, is this ball moving up or down? No. It's moving on a horizontal plane in a circle, but it's not really moving up or down. And if that's true, what does the sum of the forces in the y direction have to be?
zero.
Zero. Yeah, it has a zero out. Right? And I see two forces or force components. I see the tension partly pulling up with F sub t, we're solving for cosine 32 degrees. Right? And then minus the weight down, just 49 newtons. Okay? That has to zero out, doesn't it? Is that true? Okay. So can you guys do the algebra and solve for tension force? It's just a couple algebra steps away. Tension force cosine 32 degrees equals 49 newtons. So tension force must be 49 newtons divided by cosine of 32 degrees. Let's get a number there. 49 on cosine 30. Looking at 57.77. Let's go 78 newton, right? Now that's a lot of precision, probably too much precision. The best I could probably say might be like, well, maybe 58 newtons, somewhere in there. But I'll keep all those digits because there's still one more follow-up question, which is what's the tangential velocity? Are you guys okay so far? What we got? Okay, so while you guys are finishing writing that, digesting that, give you guys a recap. There's a conical pendulum. Like some mass is going around. I gave you enough information where you can determine everything else going on. And the questions are, what's the tension and what's the tangential velocity, so to speak? Okay. Now, you guys did figure out there's a lot of trigonometry going on, some sines and some cosines, right? And we just solved this tension by saying, well, the upper component of the tension, which is f cosine theta, has to balance out with the weight, and then there's some algebra about that. Okay. Also, along the way, you guys say, hey, we can actually determine the radius of curvature of this path by doing the length of the string times sine theta. Okay. Now, we haven't actually used that yet, but I think that might be helpful pretty soon. Are you guys okay? Up to speed with what we're doing? Okay. Now, I'll share the poster version that I made because you guys know, very first day of school, I gave you guys all these thumbnails, so you guys have this one. Okay. All right, so this has all the essential parts on it that you need to solve any question like this. So actually, we just did this one right here. Isn't that what we just did? Right? Just that? Right. And then we were able to solve for this tension force because we had everything else. Right? Okay. Now, remember how there are two forces? Now, you could add these tip to tail as one way to think this. I could take this one, tip to tail with this. Doesn't it give me a net force? Or the other way, could I take this one, tip to tail with the other? Okay. No matter how I do it, I do get this inward acting net force. So guys, is this math right here in true static equilibrium? No, because it's moving on a curved path. Right? It's always changing direction. So there must be a net force. In fact, that net force is called a what kind of force? Starts with a C. Centripetal. You guys see centripetal force, right? Okay. Which is really the combination of these two. So the net force is the centripetal force, right? And couldn't that be the tension times, guys, what am I covering up right here? Tension times what? Sine theta. Yeah, it doesn't have to be sine theta because it's opposite of theta. That would be the net force, wouldn't it? Yeah, you guys see that? See that right? Right. And the net force is acting as what kind of force did you guys just say? Centripetal? And what's the formula for centripetal? That's the answer to your lab from the last few days. It's the same thing. You see that? Okay. So I think here's the game plan for what we're about to do. If I take the tension force and multiply by sine theta, say, okay, what's this horizontal component? That is mv squared over r. Because that's what's causing this mass to stay on a curved path. Right? And we can use that to figure out the speed. And that's the connection. So let's go and do that then. So, right, picking up from here, I know that the tension force times sine of the angle would have to be the net force, which is the centripetal force, which is mv squared over r. So, yeah. For tension force, we just found that to be 57.78 newtons. Can't really precise, but save some extra digits for your middle calculations. At times sine of 32 degrees, because I gave that to you. Right? That was one of the original given values up here. Okay. Right. This is equal to mass, which is 4.9 kilograms, times v, we don't know, but we're solving for getting squared, divided by, guys, what's the radius of curvature? That's what we got over here. Yeah, you're saying, well, I think that might be important down the line. Yeah, and now it is. Yeah. That was L sine theta, by the way. Okay. But we just got that. So 0.636 meters represents that radius right there. Okay, so this is equal to this. So we have one equation with one unknown variable, which means we can solve for it. You see how this all comes together? Right? So, see, I think I have to cross multiply this radius, divide down the mass, and then take the square root. And that's the whole thing. So V equals, turns out to be the square root of 57.78 newtons, sine of 32 degrees, 0.636 meters, and then divide by 4.9 kilograms. So V equals, let's try this out then. All right, see if I can do it all in one go. 57.78 sine 32.636 over 4.9. Yeah, that looks about right. 1.99 meters per second. Yeah, I can believe that. That's it. Right. Guys, go there. Good there. Right. Again, yeah, so a little bit of complexity here because these are process puzzles, right? It's a lot of variables. If I gave you the tension and or the speed, maybe I could have asked for something else. Like, oh, I wonder what the angle is. Or, oh, that would be a little trickier to figure out, but everybody see it. Here, I got a follow-up trivia question for you guys. Okay. What do you think would happen? You can sort of figure this out. Maybe. What if I double this mass? Guys, if I make this mass twice as much, um, but I leave everything else the same. Earth gravity is the same. The length of the string is the same. Let's say we're setting up the same angle also. I want to keep that angle locked in place too. Because if you double the mass, what do you think happens to the tension? It doubles? You guys think double? Yeah, no, you could work through and show that, but that does make sense. They would have to double effectively, right? Right. What do you think happens to the speed? Stays the same. Yeah, it sure does. It sure does. Okay. Turns out that I could have made this mass anything, and this final speed would still be this. Yeah, yeah. The tension would be different, but the speed would be the same. Ooh, you can also show it too. All right. So I'm gonna here. A couple more things before I switch over to Call of Duty. Do you guys remember? I broke out this turntable the other day. I just want you guys to see this one more time before you take off for the weekend. Right. And we were saying, these 2 points right here. I lost Roosevelt somewhere along the way, but I got Lincoln and Washington stuff. And if I give them a spin, guys, do these have the same rotational motion, the same turns per time, and the same revolutions and stuff? Okay. But do they have the same linear motion, like the same distance and the same speed, linear speed? Is that the same or is that different? That's different. In fact, the further R you are, the further out from the center, the faster you'd be going and so on. Right? And the connection is if you know the angular values like theta, omega, and alpha, and you multiply by your distance from the center, r radius, right? That tells you your distance, speed, and acceleration in a tangential sense, like in a linear sense. Okay? Now you can take this here. So if you knew, but these have to be in radians, right? So omega can be in radians per second. If you multiply by r, it gives you like how many meters per second. Suppose you take v equals omega r. Could you substitute that into this v right here as omega times r? Could you do that? Right. Let's see if I can. Here, well, I'll show you guys exactly. Just save us a little time. Okay. So here's the answer to your lab. So centripetal force in terms of the speed of a point mass, right? Yeah. Like a linear speed. But what if I went this in terms of angular speed? Okay. Could I make that little substitution right there? Right? And then you do algebra, and you get a new expression for centripetal force, not in terms of linear speed, but in terms of angular speed. Do you guys see that? Okay. Now, okay, could that be good for? Well, how about those? Next week, I think I'll probably give you guys a lab that says like, I wonder how much friction there has to be on these coins to hold them in place. Right? Do you think the friction force here is acting as the centripetal force effectively? Right? And this whole rotating turntable, well, the omega is the same everywhere. Like both Lincoln and Washington here are getting the same turns per time. They're getting the same radians per second. Right? So, okay, anytime I have like a solid disk, like a solid rotating platform type, maybe it's more convenient for some methods to think in terms of not V, but in terms of omega. Right? O'Neill cylinder. Did I show you guys the clip from 2001 Space Odyssey? Okay, yeah, right. This thing was rotating in space. Okay. Okay. No, if it wasn't rotating at all, would all these people just be floating around because there's no significant gravity forces nearby? Okay. But if you give this a rotation, okay, now individually everybody just wants to move off tangent to the motion. That's Newton's first law of motion. But the wall is holding them in place, providing a normal force. That force turns out to be m omega squared times r. So their own mass times however fast it's rotating radians per second, square that, times the radial distance from the center. Okay. And if you want the sort of like artificial gravity field, which I think they all feel the same artificial gravity field, just divide by their individual mass to get omega squared r. You guys that too? Right. And so yeah, that looks kind of comparable to what you did in this lab. Right. So here's the linear speed version in terms of the point mass. Here's the angular speed version that's useful for like turntables and O'Neill cylinders. How about this? You guys see that ladder going across the diameter? What if some guy right here climbs all the way to the very center? Now he's sitting right on the center of the ladder. How much gravity? Well, it's fake gravity. There's no real gravity. How much does he feel? Zero. And you can get that right away from here because you just plug in zero, and it goes to zero. So what if he pushes off? Is it does he just float off into space? Yeah. Okay. All right.